Lab 4, the physics of extreme sports with ropes. Analysis of a swinging mass on a spring. The system model. From Newton's second law, we have the contact force of the spring and the gravitational force of the earth, giving us the net force by their vector sum. We assume no dissipation forces. For the energy principle, all the forces on the mass are within the defined system of the spring, mass, and earth, so the work done by the system on the surroundings or the surroundings on the system are zero, and thus the total change of energy in the system is zero. These are the fundamental principles that we have studied so far in the physics course. The formulas used are shown here for the spring force, for gravity, and for kinetic energy and potential energy. Also the period for a vibrating spring, which is used to calculate the spring constant and the unstretched length of the spring. The initial conditions were given in lectures 8.1 and 8.2 and from the analysis of the spring mass 1D video in Tracker. I got slightly different values than those found in the lecture, less than 1% except for L0, and I followed the calculation procedures outlined in the lecture. The initial position for the release of the spring was obtained from analyzing the spring mass 2D video in Tracker. Putting all this information into the Python code initialization and checking the calculation loop for and adjusting it for the time of observation in the two-dimensional video, we are ready to compare the trajectories from the Tracker observation with the Python model and ask ourselves, is the energy principle satisfied? Here you see a plot from the Python run showing the change in energy of the total system. E is coincident with the time axis showing no change in total energy. It's time to watch some film here. So we're going to do that right now. First up is a run of the Python model for the vibrating spring. That was presented in the lecture and is the basis of this model. Notice how closely the predicted and the observed match up, and look at the energy graph. Notice that the changes in potential energies are opposite each other, and the kinetic energy has a frequency that is twice as great as the potential energies. Now in Tracker, we can observe the trajectory of the weight as it swings and vibrates. It traces out what looks like an ellipse that seems to precess in some way, giving the complicated trajectory shown in the upper right hand side. Now on to the model that was created in Python for this motion. And we see in a moment the vibrating swinging mass and the energy graph. Notice how the energy graph is different from the vibrating up and down spring, and that now the change in kinetic energy appears to decrease and then increase, and the changes in the potential energies don't exactly match. I will rerun this, changing the plot here so that we can look at the periods in the X and Y direction. On top in green and yellow you'll see the variation between the observed and the modeled for the X direction, and on the bottom you'll see the red and the blue for the Y direction. Notice how the observed amplitude of the Tracker video decreases but but remains the same in the Python model because we did not include any dissipative forces. I also believe that this also explains for the change in the swinging here. The observed falls behind the modeled. What does it mean? For your model system, is the energy principle satisfied? The yellow plot delta B appears to overlay the time axis at 0, but is it really 0? A modification in the code to plot the delta E variation shows that it varies to a maximum of plus or minus 1.8 times 10 to the minus 5 joules, but this is several orders of magnitude less than the variation deltas in the kinetic and potential energies. Close enough to 0? Yes, but it's a pattern worth investigating. Physics is fun and fascinating. What does it mean? Here is a computation of the periods in the x and y directions. For the x direction, I got an average of 1.66 seconds. The spring swings like a pendulum with a period of 1.66 seconds. When I use the pendulum equation, solving for L, I get a length of 0.684 meters, comparable to the equilibrium length of the spring of 0.7 meters. Interesting. The y-axis period appears to be the same for the simple up-down vibration of the spring and is very consistent with what we obtained in the election. The y-axis period appears to be that of a vibrating spring. The motion of the swinging spring mass system appears to be a complex motion involving two coupled oscillatory periods, one for a vibrating spring in the y direction and another for the pendulum-like swing of the spring in the x direction. The trajectory in the xy plane appears to be a Lissajous figure, which mathematically is created by two independent sine waves in x and y. The tracker analysis appears to be a sine wave in both the xt and yt plots. This was fun. The end. Thank you.